there are several important graphic ways of thinking about linear transformations that we're going to need this semester. The first one is actually what the graph of a linear transformation looks like. So just a reminder, a linear transformation, we plug in vectors. These could be 3 by 3 vectors. We don't do that often this semester. And there should be some matrix full of constants right here like this. And it always gives us some sort of answers. I want to graph this. Now I'm going to call this graphing. Again, whoever thought of this is kind of amazing. The problem is that if I really had to graph it, you can see that I'm plugging in a two-dimensional thing, and I'm getting a two-dimensional thing when I'm done. So if I really had to graph it, I would need 4 dimensions. And somehow, some way, what we're going to try to do is just do this in 2 dimensions. But we can actually see what's going on this way. So what I'm going to do is start with the first non-trivial one, the 0, 1. The graph is ridiculous, so let's not talk about that one. I'm going to do the identity, just so you can see what sort of things we have to do, and then we'll now this is what we're going to do to graph this. First off, we have to have a little grid of points. This is the same sort of grid that you would do when you did a slope field, if you did slope fields in Calc 2. Sometimes they'll do slope fields in AP Calculus in Calc 1. But the idea is these are just nice points that I can put in and see if I can't get some sort of answers. And the idea is we're going to pick vectors to plug in, and somehow we're going to have to find a way of drawing the answer vectors somewhere. So let me put my first vector in first. Let's just put in, how about 1, 0. Now when I put in 1, 0, I'm only going to write this one once because this happens every time. Remember, this is the identity matrix. I'm going to get 1, 0. Now the question is, where on earth do I put the answer? Well, this is what we do. We go to the point 1, 0, and starting at the point 1, 0, we draw the vector answer. So we start at the point basically that we plugged in, and starting at that point, we draw the answer arrow. Let's do another one. Let's do a bunch, if we can help this. If I say t of, say, 0, 1, this is the identity matrix. I know what this does. I'm just supposed to get 0, 1. And the plotting here says go to the point 0, 1 and then plot the answer vector. So the point 0, 1 is right here, and the answer vector is going to look like this, and it's going to be an arrow that looks like that. When I plug in minus 1, 0, this is actually one of the defining properties of a linear transformation. The answer is going to be minus 1, 0. And so I go to the point minus 1, 0. I draw the vector minus 1, 0, and I get that. When I plug in the point 0, the vector 0, minus 1, the answer there is going to be 0, minus 1. And I can at least see a pattern in what I'm saying, so I'm not going to keep writing down everything what I'm going to be doing. Now, when I plug in the vector 1, 1, I know I'm going to get the vector 1, 1. And so in order to plot that, I go to the point 1, 1 and I draw my answer arrow vector there. I know what's going to happen when I plug in the vector minus 1, 1. I'm going to get the vector minus 1, 1. So I go to the point minus 1, 1 and I draw the arrow that way, and we can see that we're going to start getting arrows that look like this, and 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 this, and this, and this. And we're getting sort of a startling picture, actually. We're getting what looks like an explosion. The nice thing about linear transformations is they're very often used to model movement. And this, for example, would be a model of an explosion, which is really kind of cool. If someone said, well, explosions don't look like this. If these are the velocity vectors, they should be getting shorter as they move away. And that's true. But another way of describing this would be, for example, if I was looking at the top of the hill and watching water flow down the hill, yes, the water would flow down directly lower than the bottom, than the very, very top of the hill. And the further away you got from the top, the faster the water would be going. So I'm thinking of this as describing a landscape and actually water flowing on the landscape. All right, now let's do another example, nice and slow. If you've had too much physics, you'll see this is actually examples of vector fields, but this is where we should get our first taste of this. I want to do another example. The last example I think we actually looked at. How about if we actually put it on the top so I don't waste too much room? I want that room now. What I want to do for my second example is I want to put 0, 1, 1, 0 right in there. Now we know what that does. That switches the x and the y coordinates. I am going to want to plot points. So I'm going to have 0, 0, and 1, 0, and 2, 0, and 0, 1, and 0, 2, minus 1, 0, minus 2, 0, 0, minus 1, etc. So I'm really just picking an integer grid here. If you have a lot of algebra, you'll discover that's called a lattice. You can define that using linear algebra, but we're not going to fuss too much. Now I want some points to plot. Some vectors to plot. So I'm going to start plugging in some vectors. Yes, if I plug in the 0 vector, yes, I switch the x and the y coordinates, I get the 0 vector. Now that's a really boring one, but that's actually one of the ways we can tell that a room full of arrows like this is going to be a linear transformation, is that when you plug in 0, 0, you get 0, 0. That is an exercise in every linear algebra text. Now I want to plug in another thing. When I plug in 1, 0, we know what that matrix does to this. We saw that last time. It turns it into the vector 0, 1. Now how do we plot this again? I go to the point 1, 0 and I draw the vector 0, 1. So I go to the point 1, 0 and I draw the vector 0, 1, which goes up just like that. So that vector is the answer of what you get when you plug in 1, 0. If I plug in 0, 1, I know what this linear transformation does here. It turns that into 1, 0. In order to graph that, I'm going to go to the point 0, 1 and draw the vector 1, 0. The point 0, 1 is right here. I draw the vector 1, 0. It looks just like that. If I now, by the way, a linear transformation is going to mean, by the way, that when you plug in 1, 0, you got an up 1. When you plug in minus 1, 0, you're going to get a down 1. You can check me on that if you like. And then this is going to look like this. When I plug in 1, 1, the answer is 1, 1. So I go to the point 1, 1, I draw the vector 1, 1. And by the way, when I plug in 2, 2, I'm just going to get the vector 2, 2, so that one stays that way. If I plug in the vector 1, 1/2, 1, 1/2, by the way, I'm going to get the vector 1, 1, 1/2, 1 1/2. So every vector that's on this line is pointing away. Now when I plug in the vector minus 1, minus 1, I'm getting the vector minus 1, minus 1. And the way we plot this is we go to the point minus 1, minus 1, and we plot the vector minus 1, minus 1. And so that's just going to point this way. When I go to 2, 2, that's just going to be further and further out that way. I haven't plotted anything in over here, so let's try one like this. Let's go to the point, that's 1, minus 1. Go to the point 1, minus 1. So we're going to plug in the vector 1, minus 1. And the answer we're going to get is minus 1, 1, like that. So I'm supposed to go to the point 1, minus 1, which is right here, and I'm supposed to draw the vector minus 1, 1. The minus 1, 1 actually goes back like that, which is interesting. That's going to tell me, by the way, that this one also is going to come back like that. When I put in the vector 0, 2, it just switches the x and y components. I get the vector 2, 0. That says that this vector here is going to look like that. This vector here is going to look like this. What else can I get here? I get a vector that looks like that. Let's see here. This vector is going to come down like this. Now, what am I seeing here? Let's see here. This is the vector 2, -1, so I'm going to get the vector -1, 2, -1, 2. That's going to point back in like that. You can see that if you're off this line, the arrows are all going to be pointing towards the line every single time. So if you're off the line, every time the vectors are going to be pointing toward the line. Now we can put a more complete picture in here, but I think we can live with this for the moment. What I did say was that somehow, some way, we should be able to describe this motion. This seems a little chaotic at the moment, but it's really kind of interesting. If I'm looking down at a saddle and I drop some water at the saddle, right? If the part of the saddle that is down like this, everything goes in like this. If this is the part of the saddle that's the down parabola, right? Everything's flowing down that parabola like that. So this, what I'm really looking at here is water flowing down a saddle, sometimes down to the pit, and sometimes off that. If you don't like thinking of a saddle, think of a Pringles potato chip, because it really is the same thing. And ask yourself, what would happen if I put some water on that? It would either flow down or would flow in. And that's not just another example. I'm going to have you do one for next class period. The motion there is very, very, very clear. So you'll be happy with that one, and good luck.